First of all, if we are in classical setting, it means Stokes equation and no slip boundary condition. Then, first of all, it is not clear how this contact line, how it can advance at all, because since there's no slip, then you cannot advance as if. But really you can, because this is how a caterpillar goes. But then, the kinematic can be resolved. So you go like a caterpillar, like a tank or tractor, and if there is another fluid, then it can be ejected here along such line. And this kinematics was confirmed. But then the problem is with the dynamics, because you see here the motion in two different directions. And there is certainly a singularity, because the stress, which is proportional to the distance, inversely proportional to the distance between these two interfaces, should diverge. And more than this, this divergence is non-integrable, because there's 1 over x, you integrate it, you get 2 log. And this was famously Skip Scriven said that even Heracles couldn't sink a plate or a thing or put a finger. But we know certainly that it is not so. So what is going on? This means that if we have a classical formulation, purely fluid dynamical formulation, then really this paradox persists, because the velocity field near the contact line is multivariate. But then there are still additional problems, which were not in this, Scriven not only said this word, we published a paper which was cited much more than many deep and really important papers of him. But the problem is that you also don't know the shape of the interface. These straight lines which were in the previous slide are actually wrong, because the shape is determined by the normal stress balance. And then the dynamic contact angle will be also not equal to the static contact angle, it will be different. So it also has to be determined. So the problem is not just the singularity, and actually all these problems are tied together. And now you can modify the boundary condition, admit slip, and then this singularity is relieved. But other problems remain. How really, what is the dynamic contact angle? And also computationally, everything is very difficult because this slip length is a molecular scale, and no computing with all wonders of modern computers, nobody can compute to this scale and macroscopic body. So it is really how you really resolve it as not a fluid mechanical problem, but a physical chemical problem. So what you have to do, you have to introduce, to supplement Stokes equation by intermolecular forces. Then the interface, you can take into account that all interfaces are actually diffuse, though this diffuse region is also of molecular scale. And so there is a thermodynamic balance that determines the shape. And so the contact angle is also becomes ill-defined because it varies. And here there is a molecular precursor which is often or maybe even always formed. And so you never actually see the contact angle. When you do computations, you usually define it as an inflection point. And so then what is important is the interaction with substrate, which determines what is called disjoining pressure. I will talk about this. And here actually the structure near the substrate is very complex actually, because there is layering and so on, and also still worse, the substrate is never exactly like this, exactly smooth, but it is always rough. And so how to deal with this, with the approximations that we have to invoke to deal with this, I will mostly talk on Friday in the 2 lectures. But now I will go into very basic things. Because what you need here from this slide, you see here that you need really physical chemistry. And the liquid is a very complex medium. Because analytically or in statistical physics, you can deal with gases where the density is small, and so the finite density is a perturbation starting from the ideal gas, and also with solids where the base state is the ideal crystal, and you go into approximations on this. Nothing like this exists for liquids. And so you cannot really obtain characteristics, macroscopic characteristics of the liquid exactly from basic principles. You have to measure. And this I'm talking about a simple fluid. So simple fluid is also a complex fluid. And then when it comes to vicinity of the interface, then the simple fluid really becomes complex, because these interactions are not only inside the fluid, inside the liquid, but also with the interface. And so, and here there are 3 phases, so it's already very complicated interactions, and there is enormous amount really of work trying to resolve it from the physical, chemical point of view. But we need, after all, to go to hydrodynamics. But before, I will have I'll talk about some basic things in a fluid. Well, here are a few experimental pictures. Here, there is an additional difficulty, by the way, with the contact line, that all these are nanoscopic features which are not seen in an optical microscope, and you cannot also apply an electron microscope to liquids, unless in here are some fine nanometric experiments. Here is this contact line within a nanotube, and here is a liquid. Here is a molten alloy, and you see here, you can well see here the precursor. Then this is also metallurgical, and you see here precursor, these droplets of molten metal, and here is a precursor. Well, we can also do now molecular dynamics simulations. Molecular dynamic simulations, they also use, it's not real physics, because they use model potentials. And then, of course, the droplets, the sizes that you can resolve is nanoscale. But anyway, you see here this fine computation. you see here a precursor going off the droplet. You see here also layering. And in polymers, where the precursor is a bit bigger, so it's already hundreds of nanometers, it also can be resolved optically. So now I start really today. We see that we need really basic things about liquids, and so I start from the beginning, from the free energy functional. In taking the simple case of nonpolar fluid with van der Waals interaction, and then we see how we go through a sequence of approximations to obtain what we need for computation, what we further need for fluid mechanical computations. And I can tell in advance that these approximations are actually very rough, and they're even not justified mathematically. But nevertheless, people, and not just people, but great people who involve this, do this, and obtain sensible results that may be not quantitatively correct till the last number, but to give some reasonable qualitative picture. And otherwise, if we would be very strict, we wouldn't advance at all. So we start with this expression for Helmholtz free energy per molecule of a fluid. This is the ideal case, and this is interaction. Well, first of all, I would have to start much earlier, because you have to start with a statistical integral, then reduce it to pair interactions, which is also not really correct, not correct at all, one could say, for a dense liquid. And then we count this, and here is the interaction potential. Well, the temperature here is written in energy units. And so this is interaction with molecules. This is simple fluids, and this is the density, or at some other points. And here, this interaction potential, which depends on this distance. Then the interaction potential that that I will use here is the simplest interaction potential. So this is a Lennard-Jones potential with hardcore cutoff. Well, you can take usual with 1/12, but it wouldn't change anything. So, and then the next approximation for this, that interaction is weak outside this hard core. This is D is the diameter of the hard core. And this is a classical treatment. This is if you read Landau and Lifshitz, how they derive van der Waals equation of state. This is what happened. Van der Waals equation of state is also will meet van der Waals here again. Is also gives two phases, gas and liquids, although the interactions are considered weakly. So the next thing we start with this expression. First of all, we can, if we take here rho constant, then by this approximation, the small interactions, what we obtain is the van der Waals equation of state, which with excluded volume and with this interaction parameter. So once we're here, we derive it all, we compute this, we obtain the equation of the state diagram where you have equilibrium between the gas phase at low rho and the liquid phase at rho close to the maximum, which is 1 over d. Well, we go next. What we need really, because we don't really want homogeneous fluid, we want inhomogeneous. And the inhomogeneous fluid will also include the interface boundary between the liquid and the gas, or the vapor of this liquid. So now the same approximate formula is rewritten in such a way to include this here is what we had on the preceding slide. This is the energy of a homogeneous fluid, and this is the interactions. So if we take it, if it is homogeneous, then this term goes away. And now the equilibrium density is enforced by the minimum of this Gibbs potential, free energy. Here is the chemical potential. And we take, when we vary this integral, we obtain Euler-Lagrange equation for inhomogeneous fluid, which here this is the algebraic function, which pertains to homogeneous fluid. This is a chemical potential, and this is interaction. And take a note, the integral here is outside the hard core. So this expression should already contain the profile of inhomogeneous fluid, and it should contain surface tension. And this is really, we can obtain it. How to obtain it? We take and we integrate along levels. So this is a molecule, and we integrate the direction between these molecules and all molecules along the level of constant density. This is what we do, and there is some portion is needed to integrate it to outside the hard core. This fixes the limit. And this is the way what was done still in the more than 50 years ago by a great scientist, by the way, and much longer than that I'm telling you now. So by integration, we obtain such an interaction kernel which lumps interaction with all the layers. And this is, you see, it will be z minus 4. From minus 6 we came to minus 4. This is the same equation already in dimensionless units, and we can solve it. How to solve it numerically, and numerically we can obtain a profile of this. And what is important here is how the tail of this profile goes. The tail we can analytically prove that the tail goes like 1 over z cubed. So and this region is the interface. This is the diffuse interface. More than this, this interface where the density changes carries energy, and this And this energy we can compute. And so here what you see is the formula for the surface tension. And once we know the density computed here numerically, we can obtain the surface tension with all approximations that we have. Now, what is really surface tension? Surface tension is a term which was introduced by von Segner in 18th century. So it is actually a historic term. We have here, if we have a flat interface, where is the tension? There is no tension in any way. This is the surface energy. Surface energy is really a right term for this. But surface tension is somehow more dynamic. Now, on this slide, actually is proof that surface tension is the same as surface energy. Well, energy per unit surface is the same units, by the way, as a tension. So we take now the interface which is curved, and here this z coordinate goes normally to this surface. So every profile that we computed is going in this direction. Then one can ask what happens if these profiles coincide here. Well, nothing, because we have to assume that this curvature is small. It's another approximation. And so if it is small, here where these normals intersect, the density will be constant anyway. And now we are writing now the surface energy. This now is surface energy, which is this surface tension. Now we have a change of chemical potential. Why we need a change of chemical potential? Because we want this curved interface to be in equilibrium. It is equilibrium when chemical potential is different. Well, we usually say pressure, but they are related, chemical potential and the pressure, if you have an equational state. And so we are writing this energy, and this is the metric factor, which is very important because we have to now to work with this interface. So if we know the position of this interface, we can define the tangent, and we can define surface tensor, which is defined like this. And now, when we vary these terms, when we vary the position of the interface, this does not change, and the variation of this gives the change of chemical potential times the density difference. And the main things come from varying the metric factors. And these are formulas. This is how you compute the variation of a metric factor. It's exactly like in general relativity it is done. And as a result, this variation is proportional to the curvature tensor. And so, as a result of this long procedure, what we obtain Gibbs-Thompson. That the change of chemical potential is proportional to curvature. And this is why you will need a minimal nucleus of the liquid. Otherwise it evaporates. Well, of course, you can do it. Neither Gibbs nor Thompson did it in this way. You can do it simpler by just assuming that the interface is spherical, which it approximately is. This is somehow I like such a general approach. So this is that the surface tension and the surface energy is the same. But they are the same, but with a but. We have to suppose that the interface is that the curvature is small. Small compared to what? Of course, it is compared to the thickness of the interface. So it is not so microns is already a radius of curvature micron will be already not small. Well, the time goes very fast. And when it is not small, we see here are measurements of the interface of the surface tension. And if it goes into the curvature, goes to the nanometer range, then the surface tension drops. Then the interfaces should not be close together also. If you have such two interfaces which are separated by a very small distance, and this, by the way, happens. Say when you rotate two mills, there is a cusp singularity where you have where you can what you can resolve with really taking into account that surface tension changes, and so so this needs, of course, also a change of chemical potential, pressure, and once we have these equations, we can compute and obtain the profiles. Unfortunately, it is all numerical, though it is not difficult numerically. Now we have really, now comes something difficult. That we have to bring the substrate, the solid, into the picture. And now how it changes if we introduce the interaction with the solid wall. Now we have interaction with the solid wall, which is here is again the interaction potential, which we assume to be the same in shape, only with a different constant. And here is the raw solid. But then the interactions within the liquid are different. So we'll write it like this. This will be a homogeneous part, the energy. This is the fluid-solid interaction energy. So we take into account this interaction with the solid, with a different constant, and exclude interaction with the liquid that would be in the place where the solid is. So this is this interaction color we compute well, more or less in the same way as we compute it by integrating on the layers. So all this is good again when the solid is flat and we interact along these layers. And here is what remained of the fluid interaction energy. It was like before, but now it integrated only from the surface. And so now this energy will now depend on the distance between the liquid gas interface and liquid solid interface. And the derivative of the energy with respect to this distance is the joining pressure. The joining pressure, this is what was introduced by Diraguin already in the 30s. And this, and so the joining pressure is the derivative energy with respect to this distance, it means the thickness of the layer. And we can compute it. We take this energy and differentiate it. First of all, we put here this density profile. So to obtain it, to obtain approximate expression from this large formula, we need approximation. So we assume that this profile is almost the same as it was in the without the interface, and so we use this profile and then change the variables to put the origin at the liquid-gas interface, and then differentiate one by one. This algebra really, when you look at it like this, you will not catch it. As my teacher Levich used to say that algebra, like love, should be done in practice. And what we obtain, and certainly Dragon didn't do it in this way. He was physical chemist. And in this way, we obtain the first approximation is like this. This is a constant which is called Hammockel constant, and it is proportional to 1 over h cubed. And then, if we have a next approximation, we have the second term, h6. What I have to say that with the joining pressure is a bit counterintuitive, because if the fluid is attracted to the solid, so if it is wetting, then the joining pressure is negative, because it wants to thicken. And if it is repelled, then the joining pressure, the joining pressure is a conjoint pressure, so it wants to break. And some mathematicians actually took this cube comes from the 1 over 6 in Leonard Jones, and so the next term they took 1 over 9, which comes from 1 over 12 in Leonard Jones, and this is completely wrong because this is a repelling energy. It works in a different way. Now, if for the wetting fluid, for the wetting fluid there will be enough this term, but for the non-wetting fluid, it is important to have the next term. Because then we obtain such kind of a curve for the joining pressure. So here, this is the precursor layer, which have the same chemical potential as bulk fluid at infinity. And so there is always some thickening of the liquid on the substrate. And so there can be two kind of profiles. When it goes like this, this is the solid gas boundary, which also has some thickened gas here, or maybe it is a soft layer. It can be really the thickness of this. The thickness of this layer can be even less than a molecule. In some cases, it is thick, but it is essential anyway. And when there is a liquid, and this is the liquid layer. So we have two kinds of density profile. So the time goes fast now. It is very clumsy really to work with integral equations. Can we make it simpler and make a differential equation instead? And yes, we can. And we assume that the density is changing slowly, and we can expand this, substitute it into this expression. The linear term cancels. While we integrate over r, and the next term is this, and this gives such a familiar expression with a gradient of density, and this is the coefficient which is called the rigidity. And then the Euler-Lagrange of this is the differential equation, and then it is really very simple to make it in 1D. It is very simple. This equation, the same van der Waals in 1894, he published the first diffuse interface theory. But what is wrong with it? If we take the same Lagrange, the same van der Waals formula, and expand it further to the fourth term, then the coefficient of the first term will diverge. And this is, we read really the paper of Van der Waals, so we have the impression that he knows it but doesn't tell. So local equation is different. With any power law, it will diverge sometimes. You need exponential decay. And then you see that really the qualitative character of the solution changes because this equation has an exponential tail, and the integral equation has a cubic tail, 1 over r cubed, which is really what happens with this joining fraction. Well, is it important or is this not important? It really depends on the circumstances. By I, you will not distinguish between the exponential and the cubic. But if there is a mathematics and you go for divergences, then there is a big problem. And so there is another problem still, that when you have integral equation, you don't need boundary conditions. And when you have differential equation, you need to assign boundary conditions at the interface, which is actually not trivial matter, because it is done in a somewhat arbitrary way. Well, with this, then we can have cubic modular of the positives. You can look, you can compute the same much easier, do everything analytically. Then, towards the end, now we can come at last to the contact angle. And for the contact angle, it is rather difficult again to work with integral equations. But we can. But if we pass to differential equations, then there will be a very simple equation near the contact line, this one, and here is the joining equation. Actually, this is the lubrication equation. I will talk about the lubrication approximation later with Friday with dynamics. And this equation we can solve nicely and obtain this contact angle, this deriving from expression, and this, by the way, this formula, if you expand it again in small angles, but then you obtain the Young Laplace formula, the classical Young Laplace formula. So you can do it as an exercise, since my time for this lecture is already off. And then, well, next I will talk on Friday. I will talk on how we obtain lubrication equation, starting from the diffuse interface theory, or from whatever. Actually, we can start from whatever theory we can, and come eventually to the lubrication equation. And such clever people like Dejean, you just write this lubrication equation, which has a very nice structure. It has a variational structure. Uwe will talk. I'll leave the time for Uwe he will talk more of this. And then one has to remember that after all approximations, say expression for disjoint pressure, they are all done, not only the fluid dynamics, they are all done in this lubrication approximation. And so this is somewhat like a miracle, because this lubrication approximation works under conditions when it is not supposed to work, at angles which are not really small. So, okay, this will be our scheme for resolving this paradox. You can see it here. It can be with modifying equation and modifying boundary conditions. And this slip is a too easy solution which does not resolve everything, but when we modify equation with intermolecular forces and with diffuse interface, then the singularity is resolved, and we obtain we know what is the contact angle up to uncertainty. And here comes these conclusions, actually, not only to this lecture, but to everything. This is a really complex physical-chemical problem. And then, after we already came to this point in the lubrication equation, we still see that what still remains is the scale separation. And on Friday we will really talk about how to deal with this scale separation. Because anyway, whatever physics is the contact line is a nanoscale, and if we want to compute on microns or even millimeters, then we need multi-scale theory anyway. So, thank you.
Perhaps we have time for one or two questions. Uwe, you might want to set up so we don't use too much time. Questions? This one difficulty you presented then about the asymptotic behavior being either algebraic or exponential, and it should be algebraic, but when you pass to the PDE you get exponential decay. Are there more clever asymptotics you can use to resolve that? Oh, nobody's done that.
No, if we have equation second derivative, that's what it gives.
Yeah.
I don't know really of anything else. So
You showed
it's really
expansion.
it's a good question. It would be really good to invent something to modify this state.
Other questions? You'll need to pass over the microphone.